All right, this is 4.4, Congruence and Transformations. Essential question: what conjectures can you make about a figure reflected in two lines? What you will learn is how to identify congruent figures, describe congruence transformations, and how to use theorems about congruence transformations. All right, next we have this definition or biconditional statement. Two geometric figures are congruent figures if and only if there is a rigid motion or a composition of rigid motions that maps one of the figures onto the other. Congruent figures, if you remember, have the same size and shape. So here we got some examples of congruent figures and non-congruent figures. All right, so let's look at an example. Example number 1 says identify any congruent figures in the coordinate plane and then explain why they're congruent or how we got the different shapes. We'll start off first with this square NPR right here. I do see another square up here, the square ABCD. They're congruent because they have the same size, same shape. So I would say that square NPQR is congruent to square ABCD by a translation. The rule for it, we'll do XY has a translation. We went 2 units left, so that's going to be X minus 2. And then for our Y values, we're going to go 6 units down, so that means Y minus 6. Okay. Now looking at this, I have some triangles here. Looks like this triangle KLM is a reflection of this triangle EFG. And looking at the sides and the shapes of it, it's the same. So we would say triangle KLM is congruent to triangle EFG by a reflection on the x-axis. And then I have these two triangles here. Looking at those, I could say that this is going to be, well, let's go ahead and make the congruent statement. We'd say triangle STU is congruent to triangle HIJ. And we would say that these are congruent by a 180-degree rotation. Okay. So you're going to have to look at these different shapes and you're going to have to come up with some rules or the different transformations like a rotation, reflection, translation, and how you got from the pre-image to the image. All right, here's some more vocabulary. Another name for rigid motion or a combination of rigid motions is a congruence transformation because the pre-image and image are congruent. Now remember we said a rigid motion was moving an object without changing its size or shape. So I can kind of use these terms interchangeably. I can say a rigid motion or a congruence transformation, and they both mean the same thing. All right, so here's an example of what I'm talking about. I have this parallelogram ABCD and this parallelogram EFGH. Now I have to figure out a way to get this shape here down into this position, into this quadrant number 3. And so I have to use a set of transformations or composition of transformations to get from here to here. What it looks like to me is I would reflect here across the y-axis. And if I did it here, if I reflected it, this would be my A prime. B prime would be, that would be here, B prime. D prime would be here. And then C prime would go there. Okay, So if I reflected it across the the y-axis, and then I could translate it to go from C prime down to G, that would be 4 units down. For each of these points, B prime to F would be 4 units down, D prime to H is 4 units down, and A prime to E is 4 units down. It would be a reflection on the y-axis, followed by a translation of 4 units down. All right, now we're talking about, or we're looking at some theorems, and a composition of two reflections results in either translation or rotation. A composition of two reflections in a parallel line results in a translation, described in the following theorem. So what we're doing basically, or what we're about to do, is we're looking at how we can kind of simplify some of these compositions. How, in this case, like here, two reflections is the same thing as a translation or one rotation. Or I could do two reflections in parallel lines, and that would give me the same result as if I did a translation. So let's look at what that means. All right, so let's look at this first theorem, reflections in parallel lines theorem. It says if lines K and M are parallel, then a reflection in line K followed by a reflection in line M is the same as a translation. Okay, so let's start by drawing this out and then looking at this if-then statement here. Okay, so I start with two lines K and M, and they're both parallel. So let's draw these lines. We'll call this one K. And then I'm going to draw another line here. We'll call this one M. All right. And both of those they're parallel to each other. So let's draw this symbol here for parallel. Okay, it's part of our given. And then we'll start by drawing a segment. We'll call this segment here AB. Okay, so the theorem says that if I take this segment AB and I reflect it across line K, so let's do that, and we'll have another line here, line segment. So this would be our A prime, B prime. And then I take this line here, the segment A prime, B prime, and I reflect it across line M. So that's going to put this back over here to something like this. So this would be A double prime, B double prime. And I forgot my apostrophe here. Okay, so notice the slant of this line AB. So the result of two reflections would be the same thing as me just taking the segment AB and sliding it over to this A prime, B prime. Okay, that's what the theorem says. There's two ways to get from this segment, from this pre-image to this image. I can reflect it twice, or I can just translate it once. Now, this if-then part of it, the second half of this theorem, remember when we defined a reflection, we said that the line that connects these two, A to A prime, that's a perpendicular bisector. So the distance from A to this point right here, and the distance from A prime to this point, those are congruent, and this is a right angle. Okay, and then the same thing on this other side. If I go from A to A prime, this right here is a right angle. And then I have this distance from K to M, this distance D. So this other part here, the second part of this if-then statement says that the distance from A to A double prime, so if I go all the way across, that's equivalent to twice the distance from the two parallel lines, K and M. All right, now let's look at this example 3 here. In the diagram, a reflection in line K maps segment GH to segment G prime H prime. A reflection in line M maps segment G prime H prime to segment G double prime H double prime. Also, we know that the distance or the length from H to B is 9, and the distance from D to H double prime, which is here, that's going to be 4. Okay. Name any segments congruent to each segment GH, segment HB, and segment GA. And we want to know, does the distance from A to C equal the distance from B to D? And we want to explain that. And then we want, what is the length of segment G to G double prime? Okay, well, segment GH goes from here to here, so that's going to be congruent to G prime H prime. Remember, because these are rigid motions, so we don't change the size or shape. And then we also know that this is congruent to G double prime H double prime. Okay, so those 3 segments are congruent. And now we look at segment HB. And what's congruent to segment HB? I know HB is going to be congruent to H prime B prime. Okay, because this is a reflection. And so if HB is 9, H prime to B is also 9. And then we have segment GA. That one is going to be congruent to segment G prime A. Okay, so this is my A part of the question. All right, now for question or part B, does line AC equal to line BD? Explain. The answer is yes, and the reason being is because segment G to G double prime and the segment H to H double prime are perpendicular to both line K and M. So that means that segment BD and segment AC are opposite sides of a rectangle. So they have to be equal. Okay, now for this part C, what's the length of G to G double prime? So I want to go from here all the way to here. So this is my distance. Remember that the distance from K to M, that's our D. And so this distance from G to G double prime would be twice that. So if HB is 9, that means the distance from H prime to B is 9. And then the distance from D to H double prime is 4, so that means this distance has to be 4 as well. All right, so that means if this is 9 and 4, that tells me that this distance here is going to be 13, because I would add those two. And we explained in part B that those are equal. So if this is 13, this down here has to be 13. So that means that the distance from G to G double prime is going to be equal to 2 times 13, which is 26 units. All right, the next thing we're going to look at is the composition of two reflections that's going to result in a rotation. And so we're going to look at this theorem and kind of explain what it is and how we come to this conclusion. All right, so if the reflections intersecting lines theorem says if lines K and M intersect at a point P, then a reflection in line K followed by a reflection in line M is the same as a rotation about point P. All right, and what ends up happening is that the angle of rotation is 2 times x, or 2x degrees, where x degrees is the measure of the acute or right angle formed by lines K and M. All right, so now let's draw this out so I can explain what this means. So I have 2 lines K and M that intersect at some point P. So I'm going to draw my line here. We'll call this one line K. And we'll draw a line M, and we'll make it kind of go, draw it this way. And this will be our line M. So here's my intersection point. We'll call this point P. Okay. So if I have an image of some sort, and we'll start with the segment here, call this AB, the same segment. All right, and so if I reflect along line K, I have another image. I'll get an image that looks something like this. Okay, so this would be my A prime, B prime. Okay, and then I take this line and I reflect it across line M. So kind of like what we did before. We're doing two, in this case we're doing two reflections. So this B double prime and my A double prime. Okay, so kind of like before, taking this thing, reflecting it once, and then reflecting it twice, that's going to be the same result as me taking this original segment, this pre-image, and just rotating it to this A double prime, B double prime position. Now, and the angle of the rotation is going to be equal to whatever this angle right here is. So if we let this angle be X, the angle of rotation from here to here is going to be twice that. Okay, so look, using this theorem, we're looking at example 4, and it says in the diagram the figure is reflected in line K, the image is then reflected in line M. Describe a single transformation that maps F prime to F double prime, or F to F double prime. So I'm looking at going from this blue fish here, and I want to describe this as one transformation. So since this is two reflections, one over line K and then another one over line M, I can just do a single rotation. And if this angle right here is 70 degrees, then my angle of rotation is going to be twice as big. So 2 times 70 gives me 140. So that tells me I have 140 degree rotation. And this would be about point P.